Great. Okay. My name's Suzanne Rowe. I'm from the Animal Genomics Group down at Invermay, down in Dunedin. We have around 16 dedicated scientists working on animal genomics. We have a commercial genotyping lab, and we mostly work on... Ooh, have I got two microphones? I don't need two microphones. Anybody who knows me knows I don't need two microphones. So we're working on genomic research. We look after the livestock genetic evaluations through the Sheep Improvement Limited for beef and lamb New Zealand genetics. And we develop tools and do research for any industry that comes along that we feel that we can benefit, which is why I'm here. So I'm going to give you a quick ABC of breeding. I'll try and make it brief, and I'll try not to make it complicated. You can score me at the end as to how I do. And really, we always want to know with breeding, how fast can we go? How can we get, more yield, more litres? So if we take our flock, I don't know if this works or not. If we take our flock and we line up all our animals, and the average is doing 150 litres, well, it's pretty obvious that if we've got any variation at all, we're going to have animals down here that aren't doing very well, and we're going to have animals at the top that are really doing well. And the progress that we make, the genetic progress that we make, is completely linked to how well we choose the top animals. But we don't want to choose the top animals because we fed them really well. We want to choose the top animals that are going to actually pass that merit on to the next generation. So that's what a breeding value is. A breeding value is finding the animal here that's going to pass on the most of the genetic merit that you see to the next generation. So as we can move our average up and make some money, hopefully. So if we measure an animal and we take our top milkers, we've got our top milk yields, we can just use the... that's trouble, isn't it? We can just take our top animals, but if we do that, we probably only make about 25% of the genetic gain that is possible. So what we need to do is look at how they're related to other animals and draw in information from relatives. And we do that by adding genetic relationships. Can I take this off? That sounds really bad, doesn't it? Does that sound okay, or is that... All right, okay. It's probably just sounding bad to my ears. I'm echoing. So if we have an animal that's giving, say, an extra 50 kilos of milk compared to its contemporaries, then anything that's related to that animal, we push up the prediction. We say if this animal is related to another animal, then that animal just gets bumped up a bit. Its breeding value gets raised. If we have an animal that's got less or minus 10 from average, and we've got animals related to it, then that depresses their breeding value. So what we're doing is we're taking information from each relative and we're creating a breeding value. And that prediction for that breeding value for an animal is based not only on what's been measured on that animal, but also what's been measured on all its relatives. Now the upside of that is if we get an animal that we haven't measured, it's just been born, for instance, actually we already have a prediction, because we can take the information that we have from its relatives and we can give it a breeding value, and we can decide whether to rear that animal or not. We can decide which mob to put it in. So we can either just go on relationship, as in the total relationship, is it a half sib to that animal, or we can look at specific markers. We can say, this pink marker here is clearly worth 30 kilos, and we can screen every animal at birth, and anything that's got this pink marker, well, we put to one side. We say, this animal's got more merit. So there are a couple of ways of doing it. And when we look at genetic relationships, we can have it at the most simple level, where it's just parentage. You can't breed anything unless you know what its parents are. We can have pedigree, where we know relationships between all our animals, and we've recorded from day one. We want to know what the inbreeding coefficient is. We don't really want to breed full sibs if we can help it, because we end up with depression, so we end up with other elements coming into our breeding value. And if we use genomics, if we use genetic markers, actually we can get exact genomic relationships. And that gives us a chance to be a little bit more accurate with our breeding values. And this is just a matrix that we get if we genotype. So if we have genetic markers on animals, so say we have 4 rams and 8 ewes, and we have genomic relationship matrices, then what we can see is that ram number 1 is related to ram number 2, slightly related to ram number 3, but not related to any of these ewes. So find ewes across any of these ewes. Whereas if we chose RAM number 4, we can see that it's probably a half SIB with U number 8. So we'd possibly think about avoiding that mating. So we immediately have just the information on the animals, how they're related, how we might mate them to each other, and how we might estimate breeding values. And the diagonal here is the relationship of an animal with itself. So this is RAM number 2, and RAM number 2 is above 1. So 1 is no inbreeding, and anything above 1 indicates that we're starting to move into an inbred animal. So we can look at this animal and say, well, there's a moderate level of inbreeding there, and we're going to take a good look at this guy and just be careful when we use him. This is 761 animals that we had that were pedigreed, and they're from a flock that was well pedigreed. These are good records. We were happy with them. We ran some genomics on them. And what we found is that for most cases, the pedigree and the genomic markers gave us pretty much the same relationship. But there was a bunch of animals up the side in this green oval here that had absolutely no pedigree relationship whatsoever. So they're assumed totally unrelated, and they clearly aren't. I mean, up here we're looking at parent-offspring or full SIB relationships. So what genomics does is just gives us that opportunity to pick up these relationships that we've missed, whether through poor recording or, a RAM jumping in that nobody knew about. So again, genomics is giving us that accuracy. And this is the so what slide. This is the, okay, so first of all, what does accuracy mean? When I say to somebody it's got an accuracy of 0.5, they think that means that 50% of the time we're going to get it wrong. That's not what accuracy means. What accuracy means is, for the maximum genetic gain that you could obtain in your flock, how much of it are you going to achieve? So an accuracy of 0.5 is that you're going to get 50% of the maximum. So if we go by eye or by yield, generally the amount of genetic gain we get as a proportion of the maximum is about 10 to 25%. Okay, so it doesn't matter how well you record your animals, how beautifully you measure your milk, if you're not using any genetics, you're only going to make about a quarter of the genetic gain that's possible. And that for this particular flock manifested at about 10 extra litres of milk. If you have a parent in there and you have a breeding value on the parent, that jumps up to between 0.3 and 0.4, so 30 to 40% of the gain. A couple of parents, you're approaching 0.4, 0.5. If you've got a ram and you've measured 20 of his progeny, then you're up to sort of 0.5, 0.6 accuracy, 50 to 60% of the genetic gain. You've done a really good job of choosing the right ram. If we add in genomics, the accuracy, particularly for dairy traits, in the dairy cattle industry, it's up as high as 0.9. The accuracy becomes very high. You're very precisely estimating the relationship between an animal and its contemporaries and what you expect that predicted value to be. So that's why we're interested in genomics. That's why all industries have gone for genomic prediction. That's why they spent money developing genomic prediction, because that accuracy and that speed of genetic gain makes a big difference. And as you can see here, it's the difference between perhaps gaining 10 litres per lactation and 45. And that's per ewe. So where do we fit in? I sort of, when I started, called it virgin genomics. And it's basically saying, well, we have an industry here that's small. It has no investment. How can we help it? And the MB Dairy Sheep program that was set up had no genetics. So we went along to AgResearch and said, well, hey, we really think that this dairy sheep industry needs our help. We think that it's a strategic issue. So we got some funding from AgResearch. We've actually had $250,000 over the last 3 years to collaborate with dairy sheep farmers and to develop tools. And we've basically developed snip arrays or chips that have been useful for other industries and for the sheep industry, and we've been able to apply them. And a snip array, or a chip as they're often called, is just a fixed set of markers. Someone's gone along and chosen that set of markers for you, and they've stuck it on a slide, and every time you put your animal's DNA across, it measures those markers. If they measured it in a population that isn't really relevant to yours, it won't be very useful. If it's very close, it will. So it's fixed. The development is already done. We can also use sequencing methods, which we can use in our own populations. They're more complicated, they're sometimes more expensive, but they're far more applicable. And we've been developing something called genotyping by sequencing for new species, and that basically uses a sequencing method, but it only sequences a very small proportion of the genome, and that makes it quick, simple, and cheap for new industries. And we tried both. We tried this and this in the dairy sheep industry, and actually we came to the conclusion that the chip for you guys was the way to go, just because of the investment in the meat sheep industry. So I've got 2 case studies. I've got one in goats. My talk said small ruminants. And these guys, Barry and Judy Foote, have a silent herd. They record really well. They've got many traits recorded. And they had a go at this genotyping by sequencing method. They wanted more accurate breeding values. So we went in and we took 700 animals and we genotyped them. And we looked at the markers. Actually, I'll go back there. So when we genotype them with this genotyping by sequencing, we end up with 84,500 markers, and it costs them somewhere between $25 and $30 a goat. So we've pretty much gone 0 to hero. We've gone from a pedigreed population to having 85,000 markers on every animal. And what we did was just go back and look at the things that they'd measured and look at the effect of each marker. So this is the significance of the effect of each marker, and the markers along the genome are here, so 0 up to the 85,000. And immediately what pinged out was there were a couple of markers here. This is DGAT, this is a casein variant, probably says there, that are segregating in their population that are really, really important for fat and protein. Now what they can now do, now that they know that they're there, is go back and screen at birth and pull out the ones that are segregating and that have the right gene for fat and for protein. So it was a relatively quick and simple way of screening what was important and segregating in their population. We've done a lot of work with spring sheep, and they had a dairy sheep flock with a completely unknown genetic base, no pedigrees. They put 3,000 animals together, as Mina said. They also imported germplasm from all over the world. They had daily milk records on ewes, but no pedigree information, and they had no idea in the early days which to breed from. So one of the things we could do immediately was to look at how the animals map to breed, and we can do that because we have international panels. So we could choose the animals that had the most dairy in them, and that was an easy way of starting off that elite process before we had enough information to go a bit further. This is just a similar map showing that we can map Lacoons and Awassies and East Frisians. I'm not going to dwell on that today. So we estimated the genomic relationships for them. We summarized their milk metadata. We adjusted the records for lambing date, for trials that were going on, for mob, for group information, for live weight of the ewe, for health. And we used these daily records to get an average for each week of lactation for each ewe. We fitted a fancy model. Oh. Let's go back. We got a lactation curve for each sheep. We got a total yield for each sheep. We fitted that genomic relationship matrix I told you about, and we had breeding values. So again, we'd gone from having no information on these animals from a genetic perspective to genotyping and having breeding values. And this is what those breeding values look like. And this is just to show you that even though that looks like a pretty straight line, that looks as though you could just take milk yield and you can ignore genomics. But if we look at along this line, this animal here has got a high genomic breeding value, but pretty much a 0 difference from average if you just looked at its yield. So those are the ones that we're picking out. Those are the ones that our genomic tools are for. And those are the ones that make a difference. So here we are. We can estimate genomic breeding values for the dairy sheep industry. We can estimate large effects. We have a model. It works. We know the correlations. We know the genomics behind it. What do we do now? We can't go out and estimate, as scientists, genetic breeding values for every single person. It's not efficient. And we kind of don't want to reinvent the wheel. And SIL is here. You know, Beef and Lamb New Zealand have the Sheep Improvement Limited database. It turns out breeding values on a weekly basis. It has 8.3 million animals in it. It does 2 weekly genomic predictions. So the obvious thing for us to do was to add a dairy sheep module, was to take the information that we've been collecting at AgResearch, talk to Beef and Lamb and say, hey, we've got this packaged up. how about we add it to the SIL module and you offer it to farmers? And that's exactly what we've done. So in collaboration with people that have chosen the traits that they want recorded and the breeding values they would like, we've added to the bottom of the SIL milk traits. At the moment, we're looking at fat, protein yield, somatic cells and udder score, but there are many more in the pipeline. If any of you have any strong feelings about what SIL should be recording, talk to us. But basically what this means is that when people have breeding values for milk traits, they can also have milk values for all the traditional traits that they're also interested in, such as health traits. So now and next for us is you have a SIL module. It should be ready for next season. You'll be able to take your phenotypes and put it into SIL. Now what that means is you'll have your phenotypes standardized. You'll have somewhere to store them. If you want a report, you can go along and ask for one, which means, and a lot of people I know find it really hard to keep track of their data. You can obtain regularly updated breeding values for your flock. You'll be able to compare your animals with animals in other flock as a cross-flock analyses come through. We can continue working on enhanced tools, genomic analyses, major genes. There's a new product on the market which is around about $26 per animal for what we're hoping is 17,000 markers. When we find these major genes, we're adding it on, so it's relevant to New Zealand. It's an AgResearch product, so we can make it really relevant for the New Zealand industry. And eventually, we'd like to see a cross-country evaluation so we can compare back and see how we're doing with the rest of the world. And that's me.